Lads, first thing you should spot, or welcome to the exam, first thing you should spot is that this is asking for plural, and the sorts of things you expect to be plurals are quadratics. So you need to form this trigonometric equation into quadratics. First step, hopefully we all realize that the tan of an angle, because it's the opposite over adjacent, is equivalent to the sine, is identical even to the sine of the angle over the cos of the angle. So if I put that in, I'm going to get 3 sine theta over cos theta plus 2 cos theta equals 0. And then multiplying through by cos theta, 3 sine theta plus 2 cos squared theta is equal to 0. And I need to make this a quadratic equation, and I can't deal with it, so it's very difficult to change sine into cos, but it's much easier to change cos squared into sine squared, because we know that if I have any right angled triangle, I'm going to choose one with a hypotenuse of 1 because that makes my life easy. Then this side here, which is the opposite, so the sine of theta will be the opposite side over 1, so the opposite side must be sine theta, and the adjacent side here will be cos theta, because cos of theta is the adjacent over the hypotenuse. And if you think that through, cos theta is equal to a over h. So, and seeing as h is 1, it follows that a equals cos theta, so nice and easy. But by Pythagoras we get that cos squared theta plus sine squared theta is equal to 1, which implies that the bit I want to change to cos squared theta can be used using 1 minus sine squared theta, because those are identical things. So I'm going to change this to 3 sine theta plus 2 bracket 1 minus sine squared theta equals 0. Expand it out, so it's 3 sine theta plus 2 minus 2 sine squared theta equals 0. Now I've got my quadratic, but it's not as nice a quadratic as I would like because of that minus, so I'm simply going to multiply everything through by minus 1, 2 sine squared theta minus 3 sine theta minus 2 equals 0. I've formed my quadratic. All I've got to do now is solve it. Most of the time these things will factorize. I'm going to go on to a different sheet. So my equation I had was 2 sine squared theta minus 3 sine theta minus 2 equals 0. And you guys should be quite happy using your your trusty class whiz fx991ex, but if you use it to solve this particular equation, you won't gain any marks. You must show the method that you're using, so you need to actually show a method. As I said, most of the time these will factorize, so therefore you simply look to see what the factors are going to be. Clearly I've got prime at the front and prime at the end, which makes my life a bit easier. So I'm going to have 2 sine theta in one bracket, sine theta in the other bracket, because sine 2 is prime. The only options I've got are 1 times sine and 2 times sine, and I don't write the 1 times in, obviously. I've got options of 2 and 1, and I've got to look to see how I can put them in. So I'm looking to put my 2 in there, my 1 in there. And if I put the negative sign, because this sign here tells me I've got different signs, positive and negative. Don't forget the equals 0 every time, because that is important. And what we've got now is either these two things have got to be making the thing 0. So I've got that sine theta minus 2 equals 0, which implies that sine theta is equal to 2. Now we know that that's not possible. So I'm just going to say it's not equal to 2 because it can't be. Some people would just cross that out or ignore it, but it's best to actually be really explicit and say this can't happen. Or my 2 sine theta plus 1 is equal to 0. So therefore my sine theta is minus 1/2. Remember right back at the start I said I was looking for 2 values. Now it doesn't matter to me whether you consider the curve and a minus 1/2. So I'm going to get one value there and one value there. Or I consider a cast diagram. And so I've got first, second, third, fourth quadrant. So first, second, third, fourth quadrant. I'm expecting answers here and here. Because in the cast diagram for sine, the symmetry is vertical. So most people will use their calculators at this stage. Really, this should be written as arc sine minus 1/2, but the calculator uses as sine minus 1 to the minus 1/2. The reason for that is that arc sine won't fit on your calculator keys or above your calculator keys. It's too long. That gives you minus 30 degrees. Now, minus 30 degrees simply means that it's measured that way. So we know that this is 0 or 360. So therefore, clearly this one is 330 degrees. And by the symmetry, if this was 30, that's got to be 30. So that's 180. 180 plus 30 gives me 210. So my answers are theta is 210 degrees or 330 degrees. With any trigonometric equation, always expect more than one answer. Typically, if you've got a trig equation in quadratic trig equation, you could get up to 4 different answers, depending on the values that you get from your solving your quadratic. Clearly, at this stage, you could use the quadratic formula, but that takes longer than factorizing. So think about it and factorize it, because it makes life that much easier. You can see here that I've got 180. There's my 360. Here's my minus 30. So that gives me my 330 that way. It doesn't matter whether you use the diagram, but it's good to have diagrams in.
So we'll just have a little look at a bit of GeoGebra for this question. So the green graph that you can see is the original question. Y equals 3 tan x plus 2 cos x. And you can see it's a funny looking fellow. Although in common with trig graphs in general, it does repeat. This portion here repeats here and here, and you'll notice it's repeating every 360, and then this part here also repeats every 360 as well, which has to happen because they're basic functions. There's no multiplier or anything with the x, and so if you think about your sine and cos and tan being defined on the unit circle, as you go round the circle, when you get back to the beginning, you're going to get the same values again. Now, I want to just show you one or two functionalities of Geogebra here. So, with the point, we can have a look at the different possibilities, and you can see there's one called roots. So if we choose that and then just click on the graph, then it shows us where all the values are. And so the values that came out in the question, which were 210 and 330, are shown here. So that's point D and point E. Okay, so in the question, you did some jiggery-pokery and ended up with a quadratic in sine theta. So that's going to be this one here. And you'll notice this has the same roots as the original equation, but it doesn't look the same. Just have a little think, why doesn't it look the same? Isn't it the same equation? Well, having thought about it, perhaps looked back through the working or through your own working, you'll notice that in moving from the formula, the original equation, the green one, to the quadratic that we solved, the red one, we actually multiplied through by cos theta. So if we want to make the red one look like the green one, we'd have to divide it by cos theta. And I have foolishly left the input bar off the screen, but I'm going to type it in and you'll see it come up in a minute. So I'm going to say that h of x is equal to g of x, which is our red one, divided by cos of x. And that hasn't worked. Now, why hasn't it worked? Well, if you look carefully, you'll see that for all the previous ones, I've put a little degree sign there. And that comes by clicking on the alpha, which is at the end of the input bar. And if you don't put that, then it interprets it as radians. So what we can do is we can open that up, open our alpha, which tells us about these special symbols, and then, so there's our degree sign, and when we press return, okay, so what's happened now? Well, that looks similar to the original, but not quite right. So what's wrong with it? Well, again, looking at the working, you'll notice that we also times through by -1. So what we'd have to do is to stick a minus sign in. Now if we minus a function, it reflects it. So we'll now see it looking how we want.